All right, so we're going to continue talking today about stresses and pressure. And the plan is that today we finish with overpressure, just a little bit that we have to do, and then we talk about horizontal stress. We have talked about pore pressure. We have talked about vertical stress. And there is some piece of the puzzle missing, which is horizontal stress. And we're going to get to that today. All right, so last class we reviewed total stress and pore pressure. And we said that we can calculate vertical stress fairly well. If you use this equation over here, where this information comes from well logging tools and the depth comes from the deviation survey, you're going to be always in a very good shape to calculate the total vertical stress. This measurement also has a small uncertainty because you know more or less what that value is going to be with a very small error. Remember, throughout this class, always calculate first the total vertical stress. We'll see other problems later that allow you to compute some other things, but the first thing is going to be always to calculate the total vertical stress. The second quantity to calculate, which is very important, is pore pressure. And sometimes pore pressure is hydrostatic and follows a linear trend, but some other times it's not going to be hydrostatic. Actually, most times it is not hydrostatic. And there are many reasons why that pressure may not be hydrostatic. And right now we're looking at the mechanism called disequilibrium compaction. Whenever we have something like this and that, we call that disequilibrium compaction. And this is also called under consolidation. So our objective now is to find a method in order to calculate pore pressure. We also said last class that although in very permeable layers you can measure the pore pressure more or less easily, in shales and in tight media you cannot measure directly the pore pressure. So we're going to now see a method that's going to allow us to calculate pore pressure indirectly from properties of this mixture of clay and sand or this shape. And this method is going to be as follows. Let's go again offshore, and let's imagine that from the top of the seafloor we have a shale with a mixture of clay and sand. And as we go deeper, we have our pore pressure that now we're going to assume it is hydrostatic. We have the total vertical stress, and that the difference between total vertical stress and pore pressure is what is called effective stress, and we said that's what makes the rocks get more compacted and more consolidated. All right? So let's say that these conditions are true at this particular location. My question now is, if all of this material, it is more or less the same. What is going to be the variation of porosity with depth? When you think about that, I'm going to draw a fish here just to make sure that you know that this is water and this is clay and sand. So what do you think porosity is going to be? Is it going to increase? Is it going to decrease? With depth. So it wouldn't make any sense to measure porosity in the water, right? So we're going to start over there. So with depth, the porosity should decrease, right? Because you have higher and higher stress, and the porosity will tend to decrease with depth. Sometimes in the seafloor, even when you have very loose sediments made out of clay, the porosity is so high that can be 80%, 60%. I heard some people, they call that bird poop because it's so inconsistent, right? That it looks like that. So very high porosities, as you go deeper, porosity should tend to decrease. There are many equations that allow us to capture this trend, and one of the most popular ones is one that says that the porosity is going to be related to two parameters: the porosity at a given reference stress times the exponent of beta, where beta is a parameter, times the effective vertical stress, where this porosity, reference porosity, and this compaction parameter are those fitting parameters, and usually we get these ones from the laboratory. So if you have a known material and you take it to the laboratory and you make this curve, you should be in a good position to tell what is the porosity expected at the given depth. Okay? So, knowing that, let's go now to the following case. It's a very similar case. And now, this is also clay and sand. And our pore pressure is going to increase, we know, up to here. It's going to be hydrostatic. From here, we're going to have SV. And now, we do not know what is pore pressure, okay? We know that we have the same material than over here. Let's say this one was a well drilled at one location and a very close location with the same material. We measure a porosity that, if this was the original trend, now it does something like this. So this one now is an actual porosity. What's going on? Why is the porosity now different? Why? I heard overburden pressure. Overburden pressure? What do you mean? Exactly.
The pore pressure is not flowing hydrostatic.
The pore pressure is not hydrostatic, and so what is the effect of that? So notice that before, porosity was decreasing all the time because effective stress was increasing all the time. Those two are linked to this equation. If porosity is not decreasing after that point, and even it looks like it's increasing, what do you think happened to effective stress?
It increases the same rate as overburden stress.
Up to that point, it looks like the effective stress was increasing. Remember, effective stress is going to be the distance from here to there. But look, at that point, it deviates from that trend and it starts to change. And that means that if the effective stress, if the porosity is not decreasing as expected, it is because the effective stress is not increasing as expected. So with this porosity here, somewhere over here, I would expect an effective stress, which is more or less like this, and not what we had before like that. And if that's the case, it is because now the pore pressure, it increases up to there, but at some point, it starts to change. It starts to change, and now it is not what you would expect for hydrostatic. Smaller effective stresses, like shown here, result in porosities that are not as low as expected. So then, how do you actually calculate pore pressure now? Well, you use this equation. If you know what the porosity is, if you know what these parameters are, you know what the effective stress is. If you know what the total vertical stress is, you can calculate the pore pressure. I'm going to write this down in 1 minute, but before we get there, let's answer how we actually calculate porosity. How do you calculate porosity in the field? That this is going to be the input for us to tell what pore pressure is. Which tools, logging tools, should we use in order to measure porosity?
Density log and neutron.
You could use density porosity, right? What else?
Neutron.
Neutron porosity. What else? There are many tools that you can just measure porosity.
Gamma ray and some.
Gamma ray, it's linked to the density porosity, right? There are two other.
Sonic.
Resistivity, you could use resistivity, and I also heard somewhere over there, you could use sonic. These are usually the names, actually, let me change this one. These are the actual names or labels that you will find in well logging files. Density porosity, neutron porosity, resistivity, and delta T or travel time. So with all of those, you can calculate porosity. And the workflow then to calculate this pore pressure, it will be, as I'm going to write in a minute, but let me just add here again that now in this condition, we are in what we call disequilibrium compaction. And the case before, this one over here, this one will be normal compaction. It doesn't look very well here, guys, but I'm using colors here on the paper. If you can't see the colors, the projector is not good enough. But I'm going to upload all these pages, and you're going to be able to see the colors in there. It makes it a little bit nicer to look at. Okay, so what do we do then? We use this equation, and I'm not going to solve it now, but you do some algebra, and our objective here is to calculate pore pressure out of this equation. remember that sigma V is going to be equal to SV minus PP. So you put this one in there, replace it there, move things around, and you will find out that pore pressure is going to be equal to SV, which is a known quantity, plus the natural logarithm of porosity divided reference porosity divided by beta. This amount is going to be a negative number. So always the pore pressure is going to be a positive number. And the workflow in order to calculate pore pressure, that's something that you're going to do in the first homework, will be number one, calculate SV. Number two, determine sigma V from this equation. Here I just put the entire, the final solution, but you can, sigma V is going to be this number. 3 is going to be simply, since I've already got that over there, pore pressure is just going to be SV minus sigma V. And this is going to be determine sigma V from porosity and the laboratory values. You're going to see one example, as I said, in the homework. And this is usually the regular procedure in which you will estimate pore pressure in this type of sediments. A very common procedure, for example, to estimate pore pressure and overpressure in Gulf of Mexico sediments. There is one more thing I want to say about pore pressure. And I'm going to work entirely to the example because it is in the notes over here. Let me count. Now, there are two things out.